In previous lectures, we have seen how to analyze and evaluate control systems. Now, we're going to learn how to design the controller. In particular, we're going to look at a class of controllers that are called the PID controllers. Let's look at the block diagram of a typical feedback control system. In this diagram, the plant or the process is the open loop system that we want to control, that we want to improve or add a capability to, and so on. In order to do this, we pick a sensor, here described by H of S, to use in feedback. The sensor may have some errors and noise that we describe by N of S. We take this sensor reading and compare it to the desired output or the command and form an error signal which goes into the controller, and the controller puts out the input to the plant or process, which produces then the output. Now, as the designer, you pick the sensor, you pick the configuration, and now you need to pick the controller. The PID controller has three terms. Each term feeds back the error in some form. P stands for proportional error feedback, I for integral error feedback, and D for derivative error feedback. As you can see, the proportional error feedback has only a gain. The integral error feedback uses 1 over S multiplied by a gain that we call Ki. And since 1 over S is the Laplace operator for integration, this integrates the error and feeds that back. Similarly, G sub C equal to Kd times S, since S is the derivative operator in the Laplace space. Kd times S feeds back a derivative of the error. Now, a particular controller may contain 1, 2, or 3, or all 3 of these components. If it contains only the proportional error term, then we call it the proportional error feedback controller. If it also contains the integral feedback term, then it's a PI controller. If it's, for example, proportional and derivative without the integral term, it would be called a PD controller. And a PID controller would contain all 3. First, let's look at a proportional error feedback controller. In this case, G sub C of S, the controller transfer function, is simply a gain. We're calling it Kp, and it's shown here in this position. We are going to use an example for the plant or process of a second order system, and we are feeding back the output in a unity feedback configuration with no noise, but we still have some disturbance possibly. Now, one thing to note is that there's only one parameter that will be chosen, that can be chosen independently in the controller. So we will be able to meet only one spec. One specification can be found exactly Let's first look at the open loop system. Here we have the plant or process and the input with the output. If the input is a unit step function that goes to 1 and then stays at 1, we see a simulation of the output in this plot, and we notice that this the response goes to 1 eventually. So the steady state tracking error is 0. However, it seems to take 40 to 50 seconds before this this level is reached. And this is a rather long period of time to wait in many applications. And if we can do the same thing more quickly, then we'd be in much better shape. It would be more efficient. It would save time, etc. The second point is if you have a disturbance that's entering at the input of this open loop plant, just like this response, it will have the same response as this. So a step input due to a disturbance will produce the same output here. So if you have a unit disturbance step, the output will be an extra 1 unit, and therefore we'll have a significant tracking error because of that disturbance. So let's take a look and see if we can use a proportional error controller to speed up the system and maybe reduce the impact of disturbances. Now let's look at the closed loop response. We're showing the open loop response here again for comparison with the closed loop response. This is the closed loop response when the gain is 1. This is when the gain is the feedback gain. K sub p is equal to 5, and Kp is 40 and 140. Now, the first thing that we may notice is that for each of the closed loop step responses, as the gain increases, the settling time seems to get shorter and shorter. When the gain is 1, maybe we could say that the settling time is less than 20 seconds rather than 40 or 50. But when the gain is 5, we're probably at about 7 or 8 seconds. We are at the steady state value. When you go to a gain of 40, this looks like it might be 1 second or maybe 1.5 as the settling time. So the settling time is being reduced significantly as the gain is increased. So this is an important characteristic to notice. The second point to notice is that the steady state value when the feedback gain is 1 is only 1/2, but we're still commanding the input is a unit step, so the desired output is 1, but we're only getting 1/2 here. Now, similarly, as the gain increases, we get closer to 1. This a little over 0.8. At 40, it's over 0.9, 0.97 maybe. So we're getting close, but we're still not exactly at 1. And so this produces a steady state tracking error, which is not desirable. However, if we can correct this by putting a pre-filter gain, in this case, if we put a pre-filter gain of 2, this will bring the steady state value up to 1. If we multiply this by 1.2, it'll bring it also to 1. So we can correct for this, by using a pre-filter so that it's not a real unsurmountable problem. Now, the other thing to notice is that as we went to a gain of 40, we had very nice, sharp and quick responses. But if we go really high to a gain, let's say, of 140, or higher for that matter, we get an overshoot and then an undershoot. And so the response becomes oscillatory, which is not a desirable characteristic. And this is something that we have to pay attention to so that we don't overdo it on the high gain side. So why do these things happen, these characteristics? Can we explain them using the theory that we have learned so far? Let's first obtain the transfer function from the input R to the output Y. Here we're calling it T sub R of S. And from our work before, we know that for a feedback configuration, this is the formula that we need to use in order to obtain the transfer function from input to output. If we substitute for these, for the plant and the controller, we get this, a little algebra, and we arrive at the following second order system. Now, let's see what the DC gain of this system is. The DC gain, meaning the zero frequency magnitude of the transfer function, will give us the number by which a zero frequency or a constant input will be multiplied in order to produce the output. In this case, when we put S equal to 0, we are left with the Kp terms that are given here, or we're left with Kp over Kp plus 1. Now, notice if Kp is 1, if this gain is 1, the DC gain will be 1 over 2, or a half. And that's exactly what we found when we looked at the closed loop step response. For a gain of feedback gain of 1, for a Kp of 1, the steady state output was going to a half. And similarly, as you look here, as Kp increases, this term increases, and its limit is 1. So just like we saw from the simulations, as Kp is increased, the steady state gain gets closer and closer to 1. Now, the other property was the settling time. And to see why that is happening, we can look at the poles of this quadratic, at the roots of the denominator polynomial, which are the poles. And using the quadratic formula, we know that these are going to be the poles, depending on the value of Kp. The first thing to notice is that when Kp is 0 for the open loop case, we have a pole at minus 19.9 for the minus sign. And for the plus sign, we have a pole at minus 0.1. So the slow pole is the one at minus 0.1, so that we have an exponential of e to the minus 0.1 t, or a time constant of 10 seconds and a settling time of 40 seconds. So that's why the open loop system is so slow. It has a very fast pole and a very slow pole. As Kp increases, though, this term gets smaller and smaller, and it'll, looking at the pole with the plus sign, we will go from minus 0.1 till pretty much to minus 10. So that, we'll end up with if the pole is at 10, we're going to have a time constant of 0.1. And so that is, 0.4 as the settling time. So that's going to be a very fast settling time. As we noticed, the further we go, that's what we found. However, if Kp is increased further, more than 49, as this term will become larger than that term, so the square root of a negative number will be an imaginary number. So here the poles will become complex conjugates with a real part at minus 10 and the complex conjugate imaginary parts. And if so, the system will become underdamped, and if the damping ratio gets smaller than 0.7, we're going to end up with an oscillatory response, as we found when we had the gain set to 140 here. So this explains why we're getting oscillatory step response. Finally, in order to see what happens to the disturbance response, the impact of the disturbance, let's look at the transfer function from the disturbance to the output. Again, using our formulas from chapter 4, we know that this is the transfer function for that case, from the disturbance to the output. Substituting the values for the expressions for this, we get the following transfer function, where, of course, we notice again that the denominator is exactly the same as before, but the numerator is a little different. Now, let's take a look at the DC gain for this transfer function from disturbance to output. If you substitute 0 for S, 0 here, a 0 here, so we will have, canceling the 2's, 1 over Kp plus 1. So if Kp is, let's say, 1, a unit step disturbance will be multiplied by 1 over 2. So it will be reduced by 50%. But if Kp is, say, 49, this will be 1 over 50, and a unit step disturbance will be multiplied by 1/50th, will be divided by 50. So it'll be 0.02, or it will produce almost no impact at all. And that's a desirable feature that we would like. In conclusion, we see that the proportional error feedback controller can reduce the settling time significantly and make the response faster, but only up to a point. After that, if you raise the gain higher, the response becomes oscillatory, and the settling time does not get any smaller. The other trend that we have seen is that the DC gain of the closed loop system is reduced, is lowered when we use the feedback controller. And this can be compensated by putting a pre-filter with an appropriate gain that raises it back up. Finally, we saw that the impact of disturbances can be significantly lowered by using a proportional error feedback controller, at least in steady state. However, it is not eliminated. It doesn't go away completely. For that, we will need to use a different kind of controller. But it can be sufficiently reduced so that it doesn't really matter too much. Finally, a proportional error feedback controller can be implemented very easily with an amplifier of appropriate gain. So it's a simple, relatively simple implementation. And now, I want you to work on this homework problem before you come to class next time. For the plant in the previous example, the second order plant, find the value of Kp, the feedback gain, in a proportional error feedback controller, which will result in a damping ratio of 0.8. I know you can solve this. So let's see who has solved it and who has not next class.